Welcome to the third page of notes, or the third video that accompanies the example 2 for deflection and rotation. This goes through turning the moments into rotations and finding some of the constants of integration for rotations and deflections for the span A to B. That gives this distribution of moment and these moment equations. So, we don't just want moment though, we want the rotation and we want the deflection. So, in order for us to get the rotation, we're going to need to integrate farther. We're going to have to use this equation. That the rotation is equal to 1 over the Young's modulus and the second moment of inertia times the integral of the moment. Fortunately, our Young's modulus and our second moment are constant, so we can remove them, we can pop them on the outside, and we don't need to really think about them until the very end. But we're going to integrate this right here. The rotation function from A to B is going to be a function of x1, the one that starts right here. Is equal to 1 over second moment of inertia times 6 kips, and it's going to be tempting, folks, to not write out your units in every one of these integrals, because it's going to get, the units are going to get pretty wild. And I'm just going to encourage you right now and for the rest of the semester to actually write out all of them all the time, because when you're dealing with feet to the fourth divided by KSI inches to the fourth, it can get pretty wild and hairy, and you're gonna want to have it all written down the whole time. Okay. So writing that out, minus 1.5 kips divided by 2 feet. Just go ahead and move that feet down there, why not? x1 squared. No constant integration for this one. And that's going to equal 1 over Young's modulus in the second moment. Let's bracket what we're going to do. 3 kip x1 squared minus 1.5 kip over 6 feet x1 cubed plus some constant integration. What constant integration are we on? 5? Yeah, 5. Sure. C5. And we will also have, for this one, for this other integral. Oh, you know what? No, let's go with the let's integrate this to get the deflection. Right. So the deflection is equal to the integral of the rotation, which in this case is going to be the integral of that right there. So I'll pop EI out there. 3 kips x squared minus 1.5 kips over 6 feet x1 cubed plus c5 dx, which gives that the distribution of deflection from A to B as a function of x1 is going to be 1 over EI. Don't forget that. You're going to get ludicrously high numbers if you do. Is going to be, well, that's going to be bracketed, and it's going to be 1 kip x1 cubed minus 1.5 kips divided by 24 feet x to the 4th plus c5 x plus c6. Now when we look at our boundary conditions, we don't have any boundary conditions really that pertain, oh dear, we don't have any boundary conditions that pertain to the rotation here. So we have nothing limiting C5. We can absolutely have tons of rotation at point A, we can have tons of rotation at B, and we can have tons of rotation at C. Our only limits are that the rotation at B is going to be the rotation at B, so it's going to have constant rotation. We do have boundary conditions for the deflection at point A and at point B. So we can right away look at this constant integration C6 and say, well, if we pop 0 in to the deflection equation, we better get 0 at point A, which you can't even really see. Right, so that's got to be 0. That's safe. Now let's look at the other equations.